Dr. T.V.Geetha, Professor, Department of Computer Science, College of Engineering, Guindy, Anna University. Her special interest, Artificial Intelligence and Natural Language. She has published more than 143 articles in national and international journals. She has guided around 7 PhD students. She has got Young Scientist Award from Government of Tamil Nadu in the year 2000, Chief Minister's Special Mention Award in the year 2002 and Woman of Excellence by Rotary Club in the year 2003.
Welcome to the UGC lecture series. In this lecture, we are going to talk about in this lecture on database management systems, we are going to talk about relational algebra. This is the second lecture on relational algebra. We have already spoken about some operators in relational algebra. Okay. So, we are going to have a second lecture on relational algebra, and the objectives of this lecture are to understand the derived operator intersection with some examples, and to understand different types of join operations with suitable examples. Join is an important operation as far as database management system is concerned. Of all the relational algebra operations, we are going to look at join a little more in detail, and there are different types of join also. So, already as a quick revision of what we did last time, the domain of a relational algebra is a set of relations or tables, in other words. The basic operators, there are two types of basic operators, unary and binary. In the last class we already saw these operators. What we saw were unary operators, select and project, and binary operators like union, set difference and Cartesian product. In this we are going to look at the derived operators, set intersection and join, and division we are going to see later. And as I just to remind you, relational algebra is a procedural type of language in the sense that, or a expression, in the sense that it looks at it specifies how to evaluate the expression using this formal method. Okay. So, this is a relational algebra, this we have already seen, and here we are going to look at the derived operators. Remember, for a relational algebra, the domain of operation is a set of relations or tables, and the output is also a set either a one table or tables or relations. Now, so as we have already seen the basic operators, we are going to look at only derived operators in this session, and we are going to look at the first derived operator, which is called intersection. Intersection, as far as set operation is concerned, is a basic operation, but it can be derived from the other basic operator. So, it comes as a derived operator. So, it takes a set of rows that are common to each relation, that is the meaning of intersection. And obviously, just like we have already discussed union compatibility, the relations that participate in this intersection, it is a binary operator. So, it needs two tables or two relations, these two relations that participate in this operation has to be union compatible or compatible. Okay. So, let us take the example of a simple example of RNS, two tables or two relations that are defined, and the intersection of R union S will be, so here if you look, this is A1 B1, that is not there common to this. So, it does not come in the output. A to B2 is common to these two. So, that these two are common, only A to B2 is common to RNS. So, that is the output. This is R intersection S. This is similar to how we understand intersection as far as set theory is concerned. The same thing, only thing we are talking about a two dimensional relation or a table. So, this is considered in as a compound operation, and as far as in computational power is concerned, there is no additional computational power, but this is only for convenience of representation that we use these shortcuts. and it can be basically solely expressed with basic operators. And as far as intersection is concerned, it takes two input relations as we have already seen, and these two input relations has to be union compatible. This we have already discussed what is union compatibility. Then next we have to see how to express these operators using basic operators. So, if you look here, you have R intersection S is nothing but R, one of the operators, minus the R minus S. This is considered as see if you look here, this part of it is A intersection B, the normal set theory operation. So, if you take let us take it in terms of tables, more realistic table. This is about some boats. Okay, so, you have the sailors, their IDs, their names, their rating and age, and you have two such groups, and you want to take intersection of S1 and S2. So, whoever is common in this and this will come as intersection. So, 3158 comes here also as 3158. So, only those two sailors are the result of these two relations, and the output is also a relation. So, if you look at it in set theory terms, you have table 1, intersection table 2 is table 1, only those tuples that come here will be there in the output. So, these two tables take sets and perform a set intersection. This operation is impossible unless both the tables involved have the same schemas. Remember what we meant by schemas? Schemas were having the same attributes. Okay. So, they should be of the same attributes, otherwise you cannot do intersection. This is what we called as compatible or union compatible. It is in general called as union compatible, which we already discussed in the first lecture on relational algebra. So, because both rows from both tables must fit into a single answer table, they obviously have to be of the same schema and they must look alike, in other words. So, let us take a example and see how this is done. So, let us call part 1 suppliers as, remember these operations, this is the select and the project operations. So, we are taking the supplier number from here, so only that attribute, and we are selecting only those who give the product part number 1. So, from the supplies relation, we are taking the tuples whose part number is equal to P1, and we are taking only the attribute, that is we are projecting only the attribute sailor number. Similarly, we are doing for part 2, here everything is same except that this is part 2. So, we have defined two relations, part 1 suppliers and part 2 suppliers, and we are getting the answer as part 1 suppliers intersection part 2 suppliers. This will give you all the suppliers who give you who provide part 1 as well as part 2. So, suppose you say this is part 1 suppliers and this is part 2 suppliers, which you got from this relation, then the intersection of these two will be only S4. So, only S4 supplier provides both part 1 and part 2. So, this is a simple example of where intersection is used. So, next one, another example, find the borrower numbers of all borrowers who have borrowed and reserved a book. So, now it is a little more interesting. Instead of what we are saying is we are having a borrower number associated with all borrowers, and we are looking at a borrower who also reserves a book. So, this is reserves from borrowed. Borrow is from this we can understand that borrow relation has got borrow ID has one attribute, and it has got two relations we are talking about. In the previous example we saw one relation only, that is suppliers. Here we are seeing two relations, reserves and borrows, and both reserves and borrows we are taking they may not have the same attribute or same schema, but once we project it and take out borrow ID, the result of that will have the same schema, and those two together you can intersect. So, the answer is borrowers intersection reserves. So, if you look here, we are only bothered about the borrow ID. So, borrow ID of borrows, and this is the reserves, the borrow IDs of reserves, and what all is the intersection of these two alone will come out here. Now, originally these two borrowers and reserves table may not be union compatible, but after you do this operation and put it as two new tables, reserves and borrows, reservers and borrowers, now they become union compatible and you can do the intersection. So, that is about intersection. So, basically it is a set intersection only thing we have looked a little more in detail, in the sense that we have looked at the table schema to be the same. It should be union compatible, that is what we have looked at. If you have two original tables that are not union compatible, then if you create new tables out of that which give you the similar schemas, then you can do the intersection. We saw two examples. Saw two examples here, one in which the initial tables were the same, except that you divided into something, some conditioner, and the second type we dealt with two different tables itself. Now, let us go to another very important operation as far as database management is concerned, and that is the join operation. If you ask me which is the operation as far as database management system is concerned, it is the join operation. Now, the join operation can be derived from our simple 5 basic operators. It is not that it cannot be derived, but it is so convenient and so necessary for database management system that it has been defined as a separate operator. So, as I already told you, this is the most useful and most common operation. And so, how are tables related? Tables are related by having columns in common. Two tables will have columns in common. So, it will be a primary key in one table and which will appear as a foreign key in another table. We have already discussed this as when we were talking about primary key and foreign key and referential integrity, if you remember. So, this relation between two tables, that is table 1 having a primary key and table 2 having the same key as foreign key, this relatedness between the two tables is joined together, and this is the join operation. This uses this relatedness to combine the two tables into one. So, it will take two tables and give you an output as one table or two relations. So, join is usually needed when a database query involves knowing something found in one table and wanting to know something found in a different table. So, that is what join. And join is useful because select and project work on only one table, it is a unary operator, while join work on two tables or two relations. Tables relations we are using interchangeably throughout this course. Now, let us go back to join again. As I already told you, it is a derived operator and it can be obtained from a Cartesian product. Remember, we have already looked at Cartesian product followed by a selection condition. So, suppose we are given this R1 join condition R2, where join condition is a Boolean combination of the form relation attribute operation relation attribute, that is relation attribute operation Boolean operation relation attribute, where the attributes on the left and right side can come from the left side come from R1 and the right side come from R2. So, this is the basically the R1 join operation. There are different types of join operation. I am defining a general join operation. So, this is join operation. We will combine R1 and R2 in a certain way, how it depends on the join operation, and here you can specify in certain cases what is called a join condition. This join condition, remember, R1 has some relational attributes, R2 has some relational attributes. So, the join condition will be a Boolean expression between some attributes of R1 and some attributes of R2. So, for example, R1 join condition R2. So, this can be join condition R1 into R2. So, this is equivalent to this is what the meaning is. This R1 into R2 is the Cartesian products if you look at, and this join condition is the join condition we specify with a Boolean expression. So, this join can be specified like with the combination of select and the Cartesian product. We will go into detail about that later. So, as I already told you, there is not one type of join operation, there are a number of join operations. So, one is called as theta join, then we have a equi-join, this is a particular type of theta join, then we have natural join, this is the most used join. Join is the most used operator and natural join is the most used join operator. Then you have outer join, in this you have two types, left outer join and right outer join, and in addition you have something called a semi join. So, we will look at each of this as we go along. So, this is just to give you an idea of what we mean by these things. So, let us and also the division we are covering here. So, if you look at this is T, a relation, this is U, and then you have natural join, semi join, left outer join, division and these things. We will come to this again when we come back after the break. So, now let us have a short break. Welcome back after the break. Before the break we have just seen how there are what are join operators basically and what are the different types of join operators. Now, let us take this example of T and U, two tables, and if you look at this, this is the natural join. So, here this will take A, now this is joined by B and this B. So, here the common one is only 1. So, 1 will come here. So, A 1 and X, then A 1 and Y. So, that is all. This is removed. So, this is natural join. Now, semi join is we want only the B's only to come. So, out of this we do not want this one. So, that comes here. This is left outer join, we will come into the details about this later on. Division also we will come into in the third section. So, just to give you an idea of the pictorial form of the operations. Now, let us go into each of the operations or join operations one by one. So, first let us talk about the theta join. Now, theta join is actually the join we have already defined, where we have R into R and S are two relations that are joined based on some condition. So, the condition here can be related by Boolean operations, as I have already told you, less than, greater than, and so on. Such joins are called theta joins, and these are expressed with this condition, a Boolean condition, as the subscript. Theta is put there as a subscript. So, another way of doing this. So, that is why it is except equal to, you can have anything there, that is why it is called a theta join. So, let us assume you have students and courses as two relations, and you want to relate students and courses, and you want student number to be equal to 200. Now, please note here you have student number, name and course, and you have course number and name here. Now, this theta join will take, first of all, the output of a theta join operation, the relation will have as number of attributes will be 3 of R and 2 of the second one, S, or courses and students and courses. So, you will have 1, 2, 3, 4, 5. So, you have 1, 2, 3, 4, 5. Please note here also name, here also name. So, it has been separated or differentiated with students dot name and courses dot name. So, the number is 3 attributes here, 2 attributes here, you have 5 attributes here. So, that is all, that is theta join, you are just joining these two together. Now, the condition you are putting is that the student number should be equal to 200. So, the student number is equal to 200, you will take 200 and then combine it with these two. So, you will take 200, combine it with this, you will take 200 again and combine it with this. So, that is it, that is the theta join. So, theta join, if you had not put this condition, okay, then it will be a simple, you will take each one of this and combine it together, it will become like a Cartesian product. So, here you are putting the theta condition. Okay. Now, this theta condition is a Boolean condition that you are putting. So, that is the theta join operation. Now, the example we saw, if it is an equal, it defines a relation and it can be any Boolean operation. For example, here you could have said student less than 200, in which case 100 also will come, 100 Fred PH, PH pharmacy, 100 Fred PH, CM computing. So, you would have had those two also. But if the theta has an equal to sign, okay, then you write it as equijoin. So, if that predicate is defined by an equal to sign, then you call it as equijoin. In fact, the example we saw previously was an equijoin. So, here the primary key is equal to the foreign key of this. If this is happening, then the R and S, R has a primary key and S has that key as foreign key, then that case only, so it is automatically going to take the equal condition. Okay. So, the same example, so you have here, now it is going to take course, okay, these courses as the common attribute automatically. So, this course is going to take as the common attribute. Note here that course is not a primary attribute of this, it is a secondary, I mean foreign attribute here, this here it is the primary attribute. So, what you will do is you will take this and this, and then you will take this along with these two. So, what you do here is course is equal to course number. So, if this course and this course are equal alone, it will come here. So, these two courses are equal, these two courses are equal, okay, and these two courses are equal. So, this is an equijoin. So, equijoin only those first the attributes, there should be common attributes and those attributes should have the same values, only then it is called as equijoin. This can be considered as a special case of theta join. Okay. So, this is a very interesting operation. From this we will go into the natural join. So, natural join, what you do is, please note here we had redundant data, this is the same, course and course number, but this so the number of attributes here is again the same as the number of attributes of students plus the number of attributes of courses. So 5. But now in the next natural join this redundancy is removed here because we have put the condition equal to according to equijoin, this will obviously be the same, but still in equijoin you will put both the attributes, but in natural join one of these attributes, redundant attributes, will be removed. So that is natural join. So what you will do here is you will produce redundant data to get rid of this, we use the, so what you do is you take only all the attributes except the common one will be removed. So that is the example. So here again R1 is actually students course. So from that okay and this from that you will actually only project out student number, students dot name, this is actually giving you the R1 okay, and then course. So course number which was there initially has been taken out. So the number of attributes now is less in natural join, that redundancy has been removed. So natural join is equal to equijoin except that if the common attributes are which have been used for the equijoin, one of them only will remain, two won't remain. So I mean please note it is not 1 or 2, it can be 4 attributes also coming like that if you have 2 attributes being the primary key and secondary key, I mean foreign key and all that, but that is the concept. So from theta join if it is equal condition you go to equijoin, in the in that equal condition obviously there will be at least 2 attributes which have the same values. So same 2 attributes having the same values, that is the condition of equijoin. So from that you remove the redundant one, then it becomes natural join. So that is an equijoin of 2 relations R and S over all common attributes X, one occurrence of each common attribute, list the names and comments of all clients who have viewed a property for rent. So here you have client dot client number, F name, I name, viewing dot client number, property name, property number and comment. So here what happens, everything has been remains the same except this viewing dot client number which was the equijoin condition, one of that has been removed. So that is the result. So you do not have to specify, you will have client dot client number and viewing dot client number, both on that queuing, only on that you will be doing the operations. So now we are removed that okay. So now let us look at an example, quickly go through an example. Now this is trying to tell you that this join is equivalent to a set of operations. So we are looking at that set in a quick way. So without the join operation we could start combining the 2 tables using Cartesian product. So let us assume we have 2 tables, part and supplies, you just combine it using so suppose part had 5 tuples and supplies had 10 tuples, you will have 50 tuples. So you just, and you will have the number of attributes will be number of attributes in part plus the number of attributes in supplies. So let us assume 3 and 2, so 5 into that will be your big table, that is your Cartesian product. So now contains both okay. What we know and what we want is the order date and what we want is the part description. So the supplies into part will have S number, P number, O date, order date, P number, P description and color, and what we know is the order date and what we want is the description of the part. Now the Cartesian product will have lot of noise rows okay, you can take an example and look at this, and the step 2, so that is the Cartesian product, so you will have lot of noise. Now in the second step what you do is you remove the noise rows from this, for that you select supplies into part, if these 2 numbers are equal alone you select. So now you are removing some tuples where the suppliers part number and the other one part number are not the same. So this is the result of that, where the part number, so this is a selection operation. So first you did a Cartesian product, then you did a selection operation. So this is identical rows, so that is why those 2 rows have been one of the. So what you did by the selection was you removed the tuples. Now you, in spite of that you have identical columns as we have just described. So so we get rid of this. So one of that is removed. So this is removed. One of the P numbers is removed. So you take the Cartesian product of 2 tables with a common column, then select getting rid of noise rows, then you project so that you get rid of the duplicate column, and this is called as join. So this is the join operation. This is equivalent to project, select, project is removing that operation and the Cartesian product. Now So, what we have done is we have used two tables and combined it to one. Most often the two tables will have a share a column. The shared column will most probably be the primary key in one and the foreign key in the other, and the join operation is a combination of Cartesian product, that is just to combine the two without any conditions, combine the two tables, and select is to select the rows where the two column values are equal. If that is not true, then you cannot have a join operation between those two tables, and then you have a project operation where you remove the duplication. So, we know that only rows that are now we want only those rows where some condition is satisfied. So, that can be done again. So, this is the final result of the what we want, and now let us go to the next type of join. So, now what we have seen? We have seen theta join, then a special type of that condition that we put for theta, that theta was the equijoin. In equijoin, if you remove redundant attributes, then it becomes as natural join, and we saw that the group all these can be done by a Cartesian product, a selection and a projection. That is what we have seen up to now. Now, we look at outer join. Now, equijoin plus rows of one table which do not satisfy the condition. So, that also you take into consideration. To display rows in the result that do not have matching values in the join column, we use outer join. So, if we want, so normally in a equijoin only when the two that conditions are two attributes have equal values, we are going to do the join, okay, equijoin. Now, what you do in outer join is, in one of the relations, those rows that do not satisfy that also you are going to tuples are also going to put. So, you can put the rows that do not satisfy the equal from R, then it becomes one type of outer join. If you put it from S, this side or that side of the join operation, it becomes another type of outer join. So, you have left outer join where R are retained and unmatched rows of S are padded with null, and for right outer join S is retained and the unmatched rows of or tuples of R are padded with null, because they are not equal, you know. So, you have to pad it. So, here you have, this is the left outer join and this is the right outer join. So, let us look at the example here. The same example we are taking, we have taken this example and explained all the joins, theta join, equijoin as well as natural join. Now, here you look at this, you have please note it is not natural join, it is equijoin. So, you have these two as duplicates. So, now what happens here is you are saying cos is equal to cos number. So, cos is equal to cos here and here. So, only if these two we are putting. Now, in addition to that, this though it is not having anything here, we are also putting this with, since there is no corresponding values in cos, we are putting null. So, this is the meaning of padding with null. So, this is the left outer join. Left outer join is what is the unmatched tuples of R you put in the final relation. So, that is left outer join. So, it produces a status report on property viewing. So, here you have this plus you have the same example where we take and show the output. Now, let us take a right outer join. In the right outer join what you have is only these two come into the picture. So, 100 Fred PH pharmacy, 200 Dave CM computing, and what happens is this one also has to be considered. So, here you put null. Okay. So, this is examples, some other examples of outer join. You can just look at this with the example here. So, just to look at again a right outer join example, and this is again shows the names of students from Aberdeen's and the names of their courses. So, this is an example of combining join with select and project, okay, combination of unary and join, that can also be done. This is semi join, which defines using the output of a join along with projection. So, a projection join combination is called as semi join. So, example is the complete details of all staff who work at the branch of Glasgow. This is an example of semi join. So, this is that, and along with that projection alone. Okay. So, you can have semi join of various examples. Now, let us take a simple example. This alone I want to just do in detail. These are some schemas that you have. Now, with these schemas, I have a query, print the names of employees who are working on a project name database. So, first you have to decide what are the two schemas that come into the picture. So, let us look back employee and project. So, these are the two things that come into the picture and work on. So, now you have employee, project, work on, these two are connected by employee and these two are connected by project number. If you explain this, now this is the natural join on employee number. This is extract tuples having project name equal to DBMS and the associated project numbers, that alone it takes, and then this extracts employee number corresponding to associate project numbers, and then this extracts the names of, this extracts names, this extracts tuples, this extracts employee numbers, and then the natural join of this. So, that is another example query is given, list the parts and names of parts using both the project's DBMS. So, similarly you can explain that. So, in this lecture we have seen the intersection operation and we have seen the differences between the different types of joins, which has been explained in detail, and the working of the queries have been explained. Now, I want you to do the following examples. List 2 reasons why null values should be introduced into databases. We saw in that outer join example. List the join operations of relational algebra and the purpose of each, and then what are unions, when are two tables union compatible, and I have given you a schema, the same schema we saw, and given you some additional queries for that particular schema. Thank you.